about all that.
Yeah,
It's not bad.
All right, gang, welcome back. Good to see you. This is it. Last two lessons, and it's in chapter 9. The other chapters have trig in it, so if you're here for the trig class, we'll count those. But we're going to start talking about 9.1 systems of linear equations in two variables and applications. So our objectives: identify solutions to these systems, solve them, and then last part, use them in applications. Okay? So this should be a pretty good review from last year. We're looking at the quick warm-up right there. If I had to ask you the question, if you're looking at those three graphs, and I want to know what type of solutions they have, so part A, how many solutions would that system have visually? One, right? Because it intersects once. B would be how many solutions?
None.
Zero. And then C would be?
All
the lines.
Yeah, anything on that line. Very good. So it's always important, and in this lesson it is, but in the lesson I'll teach you Thursday, your last one, the visual will greatly help you to determine how many solutions you have. Because when you have nonlinear systems, like circles with parabolas intersecting and stuff like that, the visual will help you try to keep track of things. Okay, let's get started. All right, some definitions. By a linear equation and two variables, we mean an equation of the form ax plus by equals c. So let me just underline this part. Where the constants a and b, let me put a little color with that, are not both zero. Okay, so there's just a very generic definition when it comes to linear equation with two variables, ax plus by equals c. And obviously a and b cannot be zero, or both be zero, I'm sorry. One could be zero, but not both. They don't really have an equation. An ordered pair try that again. Of numbers, x naught and y naught, is said to be the solution of the linear equation ax plus by equals c. As we're solving these systems, you need to make sure, I'll underline it, okay, that your answer is written as such. Okay, you don't want to say x equals this, y equals that. You do want to write it as a ordered pair. Because at the end, when you graph these, you're finding that intersection point. Now consider the system of two linear equations and two unknowns. No period there. So just looking at a generic system, we have just two linear equations with their coefficients of a, b, d, and e, and c and f are what they're both equal to. So graphically, we can see that these two would be lines. And we want to know graphically, like, where do those two lines intersect at. Okay. So if we can find an ordered pair that is a solution to both equations, then we say that the ordered pair ordered pair would be this guy right here, right? The x naught, y naught. So if that is actually something, if you plug them in, makes both equations true, then it must be a solution to it. Continuing, a system that has at least one solution, we'll underline that part, is said to be consistent. That should sound familiar, that word consistent. We talked about that in Algebra 2. Okay, but if you have an answer, we classify as consistent. Remember, we talked about, it was like independent consistent, dependent consistent, and then inconsistent is what we did. But in this class, we're just worried about not the independent, dependent part, just if it has an answer, we just call it consistent. If there are no solutions, the system is inconsistent. And then the last part, the solution set to a system of equations is the set of all solutions. Let me just underline that, to the system. And this will carry over to the next lesson as well. So when we talk about nonlinear systems, same thing. The solution set will be the solution set nonlinear system. Okay? Just basic vocab definitions, seeing what this looks like with some mathematical terminology. But any questions on those terms? All right, let's just jump into it now. So let's say if I give you this system, and I tell you to determine if the ordered pair is a solution to the system. And here it is. Okay. So there's a very basic, just generic system right there. And I have these 2 points, and I want to know, is that a solution to it? Now graphically, we could do this quickly. If you have a graphing utility handy, you can graph both lines and see if those points are on there, right? Done. Okay? No big deal with it. But what we could do is just plug in algebra. You know what I mean, that word. We could plug them in and see if it works. Okay? So let's start with part A. I'm going to plug 1, 1 in to both equations. So we get 1 plus 1 equals 2 for the first equation. 2 equals 2. That's a true statement. And then for the second one, we get 2 times 1. Oops. That again. Minus 3 times 1 equals 9. So we get 2 minus 3 equals 9. Boy. Yeah. Nope. That's not good. So because one of these fail, this is a big no. Okay? It is not a solution to the system. And that happens. Okay. All right, let's try 3, -1. Same thing, plug them in and see if it works for both. So let's see. We get 3 plus a -1 equals 2. That indeed is a true statement. 2 does equal to 2. And then we have 2 times 3 minus 3 is -1 equals 9. 6 plus 3 equals 9, which gives me 9 equals 9. Hey, we got something there. Because that works for both of them, must be a solution. So I can put, I'm going to put it underneath the equations over there. Okay, so the solution set is curly brackets here. That is a very bad set of curly brackets. Let's try that again. That's better. And what do we say? 3, -1? There we go. Simple enough. Any questions on that one? Perfect. Okay. So let's look, just to kind of confirm some things. The ironic part is my warm-up. I actually drew these, not even realizing it, but just going back to it graphically. Okay. And this is up to you if you want to put this in there. I mean, I think you guys are okay with it, but I just want to make sure, just establish. So if we did have a system with one unique solution, that means that it intersects at one spot. So we call that consistent. So if you'd like a visual, so this is one unique solution. Okay, a no solution problem. On color. There we go. Set of parallel lines. Oops, I didn't make those little arrows there. That's bad. Okay, no solution, which we already talked about, is parallel lines, so that's inconsistent. I'll tell you what, underneath it, I'm going to write the word parallel. So as you're solving a system, if you notice they have the same slope, don't even try algebraically to show that. Just, you can state in your answer, no solution or inconsistent because they're parallel lines. Okay? And last one, infinitely. So we just got one line. Okay. If you remember, we did call this, I'm going to bring this back. We did call it dependent. Okay. So that is when you have the same. So for instance, let me put an example underneath. If you had like 2x minus y equals 4, if I multiplied everything by 2, let's see, minus 2y equals 8. Okay, so you can see just from that everything would pretty much cancel out, and you're left with just, well, 0 equals 0. Okay, any questions on the graphical part? Sound good? Let's solve these. Okay, let's jump into substitution method. I'm tempted to put it underneath here, but I better not. That wouldn't be fair. I will say, I mean, substitution method isn't my favorite. It does have good uses depending on what they give you in the problem. It's, I think, more useful for the nonlinear stuff. But let's take a look. Substitution method. So solve the system using sub method. I number my equations, so those who've had them before know that. Okay, I think it's easier when you number things. That way, you know, if I'm talking about it or if you're trying to show yourself notes of what you did, it's easier to look at what equation you started with. So substitution method is this. Okay, and I'm going to put this in blue here. So you're going to pick an equation. And again, it's your choice which one you want to pick. Okay. And solve for a variable, then substitute it into, let's see, how do I want to word that? Pick an equation, solve for a variable, then substitute it into the second equation. Okay? Just depends on what you want to work with. Looking at 1, I think I can find x pretty quickly by subtracting 5y. that looks like the plan I want to go with. If I look at equation 2, not that it's more difficult, but solving for any one of those variables has more work. It sounds lazy saying that, but it is true. So I'm thinking equation 1. Okay, so I'm going to solve equation 1 for x. And I'm just going to write myself a note. So I'm going to solve equation 1 for x, then sub into equation 2. Now, do you have to write yourself notes? Not necessarily. It just depends. This just helps me, because if I make an error, it's easy for me to figure out where I made my error. So equation 1 is now going to be x equals 11 minus 5y. Now let's plug that in for x in the second equation. So I get negative 3, 11 minus 5y minus 6y equals negative 24. So by doing that, now I just have one variable. That's easy to solve for, right? Okay. I mean, could you solve with multivariables in one equation? You could, but that's not something you really want to get into anyway. So multiplying the negative 3 throughout, negative 33 plus 15y minus 6y equals negative 24. Combine some like terms. So this will be a 9y now, just combining those y values together. Okay. So add 9 to the other side, or not 9, add 33 to the other side, we get negative 9, and therefore we get y to be negative 1. Okay. So far so good. Any questions on that? Actually, you know what? It's not negative 1, huh? Add 33, there's no negative there. What am I doing? Now that you have y, plug it back into any equation you'd like. I think 1's the easiest, so I'm going to say now sub into either equation 1 or equation 2. Your choice. Okay, so let me flip over here now. So equation 1. So this becomes x plus 5 times 1 equals 11. I think we get x to be 6. So now I could say my solution set is going to be 6, 1. And there we go. Any questions? Substitution method. So again, if you have a system where maybe one of the variables is pretty easy to solve for, just bring the other side over and substitute. Do that. It might be a faster method for you. Okay? All right, let's try elimination method. So that was substitution. Actually, let me go back to this one real quick. So because it has a solution, then we know that graphically, since this is already up here, that it would be one unique solution, so they're intersecting at one spot. So let me just put underneath it, so we can call that, just use our vocab, consistent. Okay? All right. So now, okay, I gotta make one note here. Your textbook, which is kind of weird, they call it the addition method. Yeah, you're kind of adding, but we never really called it that before, so here's the deal. I'm going to put here addition method in case you end up hearing that more often, but we all know that this is called elimination method, because you're eliminating a variable. So to solve the system, using the addition method. There we go. So again, if you hear the word addition method, it's the same thing as elimination. Tomato, tomato. Okay, so how do we eliminate a variable? Well, here's the deal, okay? Let me just put a little note over here. So what you're gonna do is look at the x's and y's and figure out what would be the easiest to eliminate. And it's pretty much based off the coefficients, like what is the easiest to work with, okay? And typically what you want is a variable that has an opposite sign of the other variable or other coefficient in the other equation. So y has that, right? The first equation has a negative y, the second equation has a positive y. So looking at that, I'm thinking, well, why don't we just get rid of the y's? Okay, so let me write this down here. Let's see, so you're going to multiply 1 or both, okay? Because you might not need to, you might just have to multiply the first equation by something. But 1 or both equations by a value, then add them to eliminate a variable. There we go. Okay, so multiply 1 or both equations by some value, then add it to eliminate a variable. Okay? So here's what I'm going to do. I'm going to multiply equation 1 by 4, multiply equation 2 by 3, then add. Okay? Now why did I choose 4 and 3? Well, if you look at it, if I multiply equation 1 by 4, that's a negative 12. Multiply this by 3, I get a positive 12. If I add them together, they cancel out. I could have multiplied by, instead of that, I could have done negative 2 here, positive 5 there, and I get 10 and negative 10x. And you add them, you get 0. So you have choices. So your work might look different than someone else's, but you're going to get the same conclusion. Okay, so this is by 4. So this would be 20x minus 12y equals 16. Let's see, this, I didn't even finish the sentence, did I? Nope. There we go. Multiply equation 2 by 3. This will be 6x plus 12y equals 3. Okay. So on the left-hand side, let's see, those are going to cancel out, right? So I get 26x equals 19. Okay. And then divide. So we get x is equal to 19 over 26. If you have a fraction, you didn't do anything wrong. We're so used to problems coming out in nice integer answers that we sometimes forget that that's a possibility. So we're going to work with fraction, okay, which is no big deal. So now that we eliminated that, we got what x is. So now sub into equation 1 or equation 2. Pleasure. Your choice. Okay? Whatever you choose to work with. Let's see. I'm thinking equation 2 for me. Yeah. 2, 4, and 1 is a little bit better than 5, negative 3, 4. So let's do that. So I'm going to plug it into equation 2. So I get 2 times 19 over 26 plus 4y equals 1. Multiply 2. Okay, get something like this. Now I'm going to subtract the fraction on the other side. So we get 4y equals 1 minus 38 over 26. Looking good so far. Let's see, 26 over 26. So that would be 12. Yeah, negative 12 over 26. Doing some mental math there. And then last step, divide by 4. So let me do this. So dividing by 4 here, let's see, can I reduce this quickly? So that would be a 3. So this would be 1, 3. So y has to be negative 3 over 26. There we go. Okay. See, fractions aren't too bad. But again, I don't want you to feel like every answer has to be an integer solution. It doesn't have to be. So now I have to write my final answer. Let's see, I can put it right in the middle. Solution set. So 19 over 26, negative 3 over 26. There we go. Okay. So, any questions on that? So far, so good? Okay. So we did one example of substitution, one elimination. What I'm going to do next is transition into showing you two examples. One where you have like a no solution, and one we have infinitely many solutions. That way you can kind of see like how do they look and what does that look like. All right. So for this example, I'm going to put in parentheses, this is the no solution example. So we call that what? Inconsistent. So let's say 3 over 2x minus 3y equals negative 9. X minus 2y equals 4. Now if you look back in your notes, you're like, okay, which one was a no solution problem I can reference from? Now you know. We have our choice. We could do substitution or elimination. Doesn't matter. I'm thinking, let's see. Substitution wouldn't be too bad, huh? I was looking at that fraction, I'm like, well, I could multiply by 2. You know what I mean? And then go from there, but yeah, we can do substitution. Why not? So let's see, I think equation 2 would be perfect for it, huh? So let's move this over to the other side. So we're gonna solve by substitution, sub method. So I'm going to solve equation 2 for x, then sub into equation 1. Okay. So equation 2, let me just bring this down here. So we get x equals 4 plus 2y. Alrighty. So let's see, plugging that into the numerator, or not numerator, first equation. My brain's so scrambled anymore. So 3 over 2, 4 plus 2y minus 3y equals negative 9. Alright. Now even though there's a fraction there, this is going to work out pretty good. So let's see. This would just be, what, 12 over 2, which is 6 when I multiply it. Then this would just be 6 over 2, which is just 3y. Okay, minus 3y equals negative 9. Now immediately I can see that the variables, they're gone. So I get 6, maybe. There we go. 6 equals negative 9. That's not true, right? That's not true? Okay. So this is a no solution, okay? So from this, we could say therefore, okay, we have a no solution. So that's just empty brackets, and then we call it inconsistent. So what type of lines must they be for that to happen? Parallel. Yep. So it's extra, but why not? Let's put down their parallel lines. All right. Any questions so far? Think we're good? Okay, so let's do one with infinitely many. And then we should be on to the application stuff. Make it really good time. Okay, so for this example, let's put in here infinite solutions. That way we know what we're looking at. Solve the system. doing that recently. I'll be writing words down and I'm missing like a letter. But somehow my brain goes back to, like at the end of the word goes back to where I missed the letter and put it in there. I'm not even doing it on purpose. I got no idea. No idea what's happening. Well, for this one, we kind of have spoilers. We know what it's going to look like. But still, let's just try and solve it just to see algebraically what happens. And I think like over here, I think substitution would work again. What do you guys think? Think just solve for
I
y?
personally would use elimination simply because if you multiply equation 2 by 2, it just everything lines up and cancels out.
Oh, you mean like,
Yeah, if you just take equation
Yeah,
2,
we
multiply
could.
the whole thing by 2, it just all like cancels out.
yeah, why not? Let's do it.
Yeah.
I like that.
It's a one-to-one.
Okay. So, well, let's rewrite equation 2 real quick. All right, so this will be 3 over 2x plus 2y equals 6. Okay, bless you. Bless you. So now what we can do is multiply equation 2
Like negative 2.
by, negative 2.
Yeah.
Then add equation 1. What's interesting is the notes I have laid out, I've done everything different. It's like I wanted to do that, it's like, forget it, let's have fun. Let's go off the rails a little bit. Okay, so this guy multiplied by negative 2, so we get negative 3x minus 4y equals negative 12, and then 3x plus 4y equals 12. That looks like a bunch of zeros, huh? Gone, gone, and gone. So 0 equals 0. Which, that's a true statement. 0 should equal 0. Okay, so that tells me of infinite solutions, which also tells me that these two are what, the same line, right? Just two different equations representing that same line. So for this guy, okay, so infinite solutions, there is a way for us to write this out, okay, using our set notation. So let me show you how that looks, okay? So let's just put a note here. Infinite solutions, because it's the same line. So any points that are on that line will work for both equations. Okay, now how do we write this using our set notation? Well, we could do this. Let me go back to this guy up here real quick, okay? Solve one of these for y. Well, this one's almost done. So we go ahead and divide everything by 2. So this will just be y equals 3 minus 3 over 4x. Okay? So now, here's how I can write my solution set. I think, and this is the interesting part, with mathematics, there's so many different ways you can write things. So I don't want you to feel like you're incorrect if you just write infinite solutions, but I want you to see some of these other methods. So first, it's just x. Okay, you probably think, well, shouldn't we put something in there? Well, no, because it would be every x value that's on the line. Then we put the y value, so it would be 3 minus 3 over 4x. Given that x is a real number. Oh, nope. We want the brackets. There we go. Okay, so this is what it's doing. So if I were to plug, let's say 1 in here, then you're telling the reader to plug 1 into here, you get your output, that's a solution. If I plug in negative 1,000, you plug negative 1,000 into here, that ordered pair would be a solution. So that's you actually showing the reader like what all of your answers are going to look like, okay, in that format. So again, the first value is always going to be an x because you're just plugging any real number you'd like. That's why we specified over here, just real numbers, no complex, you don't want i's, okay? And then here, to get your y coordinate of your solution, well, that's just this guy over here. All right. Any questions? All right, let's do applications. So I got 2 application problems, and that's it. Okay, here we go. Applications. history student can obtain two acid solutions from the stockroom. The first solution is 20% acid, and the second solution is 45% acid. Okay? And I'll put here the percents are by volume. Okay? So there we go. We got two acid solutions. One has 20%, one's 45%. How many milliliters of each solution should the student mix together to obtain 100 milliliters of a 30% acid solution? Okay. So we have these two solutions, and we're gonna mix them together. Play mad scientist here for just a short bit. And I wanna get 100 milliliters at the very end, that's 30% acid solution. Because I need it for some experiment, let's just say. Don't know what experiment you need it for, but we need it for something. Well, one of the things you can note is we need some variables, right? Okay, let's define some things. I don't know how many milliliters of 20%, 45% I need. Don't know. So that's gonna be my variables right there. So I'm gonna let X be the number of milliliters of 20% acid solution. And then we're gonna let Y be the number of milliliters of 45? Yeah, 45% acid solution. Okay? So yeah, just define your variables. Now, looking at this, I do see two topics. The first topic that's coming to mind is this guy right here. We have a certain volume that we want to use. Okay, we want 100 milliliters. So if I take the X solution and the Y solution, they should add up to be 100. So there's one equation down. My second equation is going to come from the concentration amount, right? The 20%? Yeah, 20%, 45%. So let's go ahead and write this down. So we need, let's see, X was 20%. Okay, so 0.20X and then plus 0.50Y. Now here's the good news. I actually know the percent I need for the 100 milliliters. I need 30%. So right here, okay, if I take 30% of 100, you get 30. But let me just go ahead and put how I got that. So I took 30% of 100. When you do some sort of mixture problem like this, it's always your percent of what you need times your volume here. So I actually know what that's going to be ahead of time. By the way, I'll put over here. Or, if you don't like that, you could, okay, set the 30% equal to X plus Y. So you could do something like this. That requires a little bit more work, more steps, okay, which I actually did. And it's not terrible, but I think it's easier if you already know the volume and the percent, go ahead and multiply them together. So those are my two equations. Now I just gotta solve it. So honestly, the hardest part of these problems is just setting up your equations. I don't like decimals. I shouldn't say that. Decimals aren't bad, they're friendly. But I wanna make it to where I can work with those equations more efficiently. So I'm gonna do an extra step here. And you can do this, by the way, because they're still equivalent. If I multiply that whole thing by, let's say, 10, would that help us on the decimals? Like 0.20 becomes 2 now, and then you get 4.5. That's a little easier to work with. So that's what I'm going to do. So I'm going to multiply this by 10. No reason, just to, again, make the calculation somewhat easier. So just erase that. So this is now going to be a 2x. This would be a 4.5y. This is going to be 300. And then I'll put equation 1 above it. Okay? So I didn't really change any values there. I just tried to make it easier. Now, I'm thinking to use elimination here. If I multiply this by a -2 and add to this guy, the x's are gone, right? So that seems like a good idea. So I'm going to multiply equation 1 by -2, then add. Okay? Now I could have left it, again, I could have left it like this and multiplied this whole thing by -0.20. That's okay. We're going to stick with integers. Okay, you know what? I'm not going to do that. We're going to put it on the new board. I'm not going to squish it all in one little space. Okay, so let's see. We get 2x, -2x, minus 2y equals -200. 2x plus 4.5y equals 300. The x's are gone. This will become, what, a positive 2.5y? And over here we get 100. Hey, that's not too bad now. So we'll divide, and that's 40. Now what did we find? Oh gosh, I can't talk. We found the number of milliliters of a 45% acid solution we need for our mixture that we want at the end. So what do we do now? Well, we just plug this back into either equation. I think 1 looks like the easiest. So we get x plus 40 equals 100. So x must be 60. So here's what I'm going to do. Let me go ahead and write this in context. Okay, I'm not going to write it as an ordered pair per se or anything like that because we actually have something here to work with. So what I'm going to say is the student needs, let's start with x. It's going to need 60 milliliters of the 30% solution and 40 milliliters of the 45% solution. There we go. Okay. Any questions? Last one. Yeah.
That 30% should be 20%.
20%? Oh, yes it is. Thank you. Thank you. Now, let's talk about motion. Uniform motion. Let's talk about boats. Boats are fun.
Lieutenant Dan.
Alright, we have a boat. It has traveled 288 kilometers. Okay, each way, downstream, and upstream. Okay. The trip downstream took 12 hours. It's a long trip. The trip back took 24 hours. You know what? I changed my mind. Boats are fun. That's a long time on a boat. 24 hours? Heck no. What is the speed? Of the boat? No, I haven't been on a cruise. But I will say, Netflix had a documentary. Did you ever see that? It was Poop Cruise. Never again. Nope. That whole fleeting idea of me wanting to be on a cruise is like, that's gone now. That was an awful experience. Anyway, what's the speed of the boat in still water? And then, what is the speed of the current? Did you know those people still went on cruises afterwards? That's what's crazy. You just had a fire that just stranded the boat. You were going to the bathroom in baggies, and then when they towed the boat, all that stuff from the toilets and stuff came out. It was rushing everywhere over the deck. It was disgusting. And still, people went on cruises after that. That's okay. Don't think it'd be fun. Okay, now looking at this, let's think about something. We know from many moons ago that the distance that you travel is equal to how fast you're going times the time. Okay? So we're going to use that to help create our formulas here. Let's define some variables. One of the things I don't know is how fast the boat's going just in still water, right? Like there's no current whatsoever. So what I'm going to do is let B, okay, be the speed of the boat in still water. So B for boat. How about that? And for current, I'm going to use what letter? C. There we go. Speed of the current. I was going to mess with you and say Z, but nah, we're not going to do that. You could, by the way. You can use any variable you'd like. Now, I'm going 288 kilometers each way. Okay, that's a good thing. So, looking at this, so 288 equals. Now, let's think about one way at a time. So, let's say you're going downstream, okay? So, you're going with the speed of the current as well. So, the R part would be the B plus C, and then the time downstream was what, 12? Okay, it was 12 hours. So, that's my first equation. Okay, so if you want to put, I don't have space. Well, maybe I'll put it over here. So, this would be the downstream equation. Okay. Now, the upstream, I'm still traveling 288 kilometers, but now it's the boat against the current, so those two rates subtracting each other, and this time it took me 24 hours, so this would be the upstream. Okay? So those are my two equations.
Does it say times 12 or minus 12? What is that?
It's times.
Times, sorry.
Oh, times. Oh boy.
There we go. Okay, any questions on how I set that up? And it's gonna be the same with any form, like if these were airplanes, you'd still do it with airplanes, right? Except you maybe use A for airplane speed, not B. Okay, now, how do we solve these? Well, what I would probably do first is just distribute, see what the equations look like. So down here, let's see, the first equation is gonna be 288 equals 12B plus 12C. The second equation would be 288 equals 24B minus 24C. Okay? So that's what I would do first. Just multiply it out. Now we have two methods, substitution or elimination method. I think elimination method would be great. Because if I just add them as it is, well not add them, but if I multiply the, what, top one by 2 and add them, I think we get rid of the C's. So let's do that. So I'm gonna multiply equation 1 by 2, then add. Okay. Or could we do, you wanna take half maybe? That'd be smaller numbers. Let's do the smaller numbers. Let's do that. Let's do some smaller values. So we'll take half of equation 2 and add it. Not that it would have made that big of a difference. But anyway, let's see, we get 288 equals 12B plus 12C. This would be 144, 12B minus 12C. Okay. This is looking good. So this would be 432. Those are gone. No, they're not gone. They're here. I lied. That's 24B, but those ones are gone. There So C's are gone, and divide. So the boat speed was 18. Okay. Now, gotta find the other one. So we just gotta what, plug that back in? Any equation we'd like, okay? Really doesn't matter, so I'm just gonna pick the first equation, no reason. So let's see, the first equation would be 288 equals 12 times 18 plus 12c. So multiply, subtract it over, we get 72 equals 12c, so that must be 6. So the current was 6 miles per hour. So let's go ahead and actually formally write that, because again, I don't have a set of lines I'm really concerned with, I'm actually having some context with it. So here we'll say the boat's speed in still water is 18, I said miles per hour, I forgot it's in kilometers. So kilometers per hour, and the speed of the current is 6 kilometers per hour. And that, my friends, is systems of linear equation in two variables. Questions? You guys are awesome.